I'd like to discuss the error term in Simpson's rule. Since Simpson's rule is based on interpolation at 3 points per double subinterval, the function value is exactly the polynomial plus a term that has a cubic in it. One expects the local error to be delta x cubed, but it turns out to be better than that. We can expect this sort of thing, though, because Simpson's rule is based on using 3 points, but one of them is in the middle of the interval. Based on what happened with the midpoint rule, we expect better behavior. So let's see if we can't figure out how this is going to go. Suppose that instead of just using points x equal a, x equal b, and x equals c, that we toss an additional point in. We'll call the location of that point x equals z. This will alter our Newton table by having a row that has z and the function value with z. And once we have those, we have an entire new row of coefficients. The polynomial used in interpolating to get Simpson's rule is based on this for its constant coefficient, this times x minus a, this times x minus a times x minus b. With the addition of this point z, we'll just have an extra term, f bracket abcz times x minus a, x minus b, x minus c. When we integrate, the difference between the new method, the one that includes the z, and Simpson's rule, will come from that last term. Without actually calculating the divided difference, we will regard that at the moment as some constant. I want to figure out how the new approximation is going to differ from just doing Simpson's rule. From a previous discussion, we already know that Simpson's rule is given by delta x over 3 times f of a plus 4 f of b plus f of c. When we go to this new method, which includes point x equals z, we'll have an additional term, f bracket abc z times integral from c to a, x minus b, x minus c dx. This term is the improvement over Simpson's rule by including point z. Let's look at the integral involved in this new improvement. The integral from a to c, x minus a, x minus b, x minus c. We are integrating a cubic polynomial. It will be convenient for us to change variables. I'm going to let u equal x minus b, from which expressions for x minus a and x minus c can easily be found. If I choose to use u as the variable in my problem, then I have to figure out the appropriate limits of integration. When x is a, u is the negative of delta x, and when x is c, u is delta x. The derivative of u with respect to x is 1, so du will be the same as dx. Consequently, the change that I get from Simpson's rule to the new and improved rule will be the integral from negative delta x to positive delta x, u plus delta xu times u minus delta x, integrated with respect to u. After doing the algebra and then the antiderivative, which turns out to be an even function of u, So that means when you evaluate it at delta x and negative delta x for the u value, you get the same quantity. A number minus itself is 0. So how does Simpson's rule in its value differ from Simpson's rule plus this extra point x equals z? It does not. It is the same result. Even though the interpolating polynomial between using a, b, and c for x values and using a, b, c, and z for x values are different, it turns out that the integral of those quantities over the interval from a to c are the same. This means the difference between the true value of the integral and what you get from Simpson's rule is the same as the difference from the true value of the integral and what you get from the Simpson's rule plus an extra point method. Therefore, the error in the interpolating polynomial for Simpson plus z is the fourth derivative over 4 factorial x minus a, x minus b, x minus c times x minus z. The error in Simpson's rule plus this extra point is given by this integral. Despite appearances, this does not depend on the value of z. We've just convinced ourselves of that. I'd like to calculate this integral, which doesn't depend on the value of z, but there's something in the way. X minus z will change sign somewhere in the interval, so I can actually just use the mean value theorem for integrals. On the other hand, since this doesn't actually depend on the exact value of z, I can resort to trickery. I can select some small positive number epsilon and let z equal to b plus epsilon, and this formula will be true. I can let z be b plus epsilon over 10, and this formula will be true. I can let z be arbitrarily close to b, and the error formula will be true, meaning I may as well take a limit as z approaches b, epsilon tends to 0, and my error estimate will still be correct. As a result, I can state that the error in Simpson's rule, which is the same as Simpson plus an extra point, which doesn't depend on the point, must be the integral from a to c of the fourth derivative at alpha I over 4 factorial times this product of factors x minus a, x minus b times x minus z. I've allowed the z to approach b though, so that's just x minus b squared, times x minus c, integrated with respect to x. In the double interval from a to c, x minus a is non-negative, x minus c is non-positive, and the middle factor, as it's squared, is non-negative. This product of factors does not change sign on the interval from a to c. Since it's a polynomial, it is integrable there. If I assume the fourth derivative of f is continuous, now I can use the mean value theorem for integrals. Unlike the previous integral, which had only a first power on the x minus b, this integral, the one involved in the error for Simpson's rule, cannot be 0. We are integrating something that never changes sign. So we must work this integral out. If you do the same substitution as before, u equal x minus b, you'll be led to the integral from negative delta x to positive delta x, u plus delta x, u squared, u minus delta x, du. Evaluating this is straightforward, but note this time, after finding the antiderivative, you have an odd function of u. Putting delta x and negative delta x in for u will not result in cancellation, but rather reinforcement. When all is said and done, this integral simplifies to negative 4 over 15 delta x to the 5th power. The error in Simpson's rule, which comes from using parabola number I, is the fourth derivative at beta I over 24, 4 factorial that is, times negative 4 over 15 delta x to the 5th power. After combining terms and factors, this is negative 1 over 90, fourth derivative at beta I times delta x to the 5th power. In our previous methods, there was one point that we looked at per subinterval, but we're doing something a little bit differently here. We have n subintervals, but we need 2 to make one of these quadratic interpolations. So there are not n of these things to add up, but rather n over 2. The total error is negative 1 over 90 times delta x to the 5th power times the sum I equal 1 to not n, but n over 2, value for the fourth derivative at beta I. Using the same fact that we've used before, I can write the sum in the brackets as n over 2 times some value of the fourth derivative. Doing as we did before, split one of the 5 factors of delta x out and write it as b minus a over n. Simplify, and we obtain what's the usual formula given for the error in the Simpson's rule. This was quite tricky because it was centered. Coming soon, how to program this in an efficient way. Until then, I hope everyone has a good day. I'll be seeing you again soon. Just as the midpoint rule was. Soon, how will we program this? And how will we do wow, 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 wow.